the concept of continuity is pretty straightforward. If I want to talk about how a function is continuous, I want to say start at A, start at B, and draw a continuous function from A to B. All right, well that just means I have to get to B without picking up my pen. That's it. That function is continuous from A to B and for any point in between C. Okay, intuitive definition, pretty easy. It just continues along the curve. The formal definition, well here's another one. This one's continuous. That is length versus time. So this could be the growth of, I don't know, some kind of animal over time in years, and it kind of levels off like humans do. Would be continuous from the time of birth up until, well, whatever we are here. Okay, continuous for all values t. How about this crazy function? Looks like this. Is it continuous? Well, I would guess so. It looks continuous. I wouldn't pick up my pen. But you say, well, what's going on at 0? It looks like there could be a problem at 0. And then, does this take care of that problem? By defining 0. Okay, so what we need then is a real definition. And the definition's not bad either. So the formal definition looks like this. So think about it. Does this make sense? If the limit as x approaches some value for your function is the same as the function value. So this is like a calculus thing, right? And this is just your function value, f of a, some output. So are they the same? Well, in order for this to be true, then this has to exist. Okay, so we can even break down. This is really the only thing I need to prove continuity. So like back to my is this function continuous? That is, for each value in here, for each x value, does the limit, as you know, or informal definition, as you approach this, does the limit equal the function value? And it's pretty clear that that should be the case, right? Here's maybe it's easy to see of an example where it's not true. You would say this function's not continuous at x equals a. Right, because I had to pick up my pen and skip this point. Right, it's defined for all values from 0 to, let's say, b. It's defined along here, and it's defined at a up here. Right, but it's not continuous because the limit's down here, the function's up here. Okay, so that means it would not be continuous by a formal definition. Informally, there's a jump in the graph. Formally, the limit as x approaches a does not equal f of a. So therefore it's not continuous. All right? So in order for that definition to be true, these three check marks are just a breakdown of this definition. So f of a has to exist. Check. Defined. The limit has to exist. Well, that's kind of clear here. That has to exist if they're equal to each other. And then, of course, they have to be the same. So really the definition, just kind of jump to this one because this and this go in number 3. Okay? So if I ask you to discuss the continuity of this, my informal definition is straightforward. It's continuous on 0 to 1, not including those. And then from 1 to 2, and then from, we'll talk more about at the end point, but you can kind of get the idea. It's similar to like being defined there. 3 to 5. And then from 5, not including 5, to 7. Not including that. Now you might ask yourself, what's the difference between this and the domain? It's pretty similar. This reminds you of domain. However, look at what's going on at 2. Right? It's not continuous at 2, but it is defined there. Right? So therefore it's not continuous because the limit would be down here and the function output's up here. So that's by definition not continuous. By intuition, obviously not continuous. There's a hole in my graph. All right, a couple properties that are pretty straightforward. If f and g are continuous, then their sum is. Constant multiple times one of them is. The difference is continuous. The product is continuous. You raise it to a power, it's continuous. And the quotient is continuous, of course, provided that the denominator is not 0. Okay, so you picture polynomials. They're nice, well-behaved functions, continuous for all values. Rational functions, for the most part, they're well-behaved, except the issue, of course, is when this is 0. So they're going to be continuous for everywhere except when the denominator is 0. Here's an example. Right, if I factor this denominator, I get x, two numbers that multiply together to give you 12, and add together to give you -7 will be that. So it's not defined at 3 and 4, and also not continuous there. But everywhere else is what those previous definitions. Continuous everywhere else. Same as the domain for rational functions. Right continuous is a little tricky, I think. It's coming from the right. It's continuous. It's not really that important. It's just the term right continuous. You would say this is continuous. I ask you, where is it continuous? You say from A to B, and you include A, right? And that means right continuous, because as you come in from the right, it's continuous. Kind of like a limit. We said that about limits. Left continuous, straightforward. Continuity endpoints, does this make sense? So here's the real calculus piece. If the limit as you approach A from the right is f of A, then you have continuity from the right. So back here, the limit as you approach A from the right, does that equal, right here, that's f of A, right? Does that equal f of A? Yes, then it's right continuous there. Okay? Pretty straightforward. Discuss the continuity. Oh, it's continuous from -infinity to 0, include it. And then it's continuous from 0 to infinity, do not include 0. And you would call this function at 0, is it left continuous or right continuous? Well, it's left continuous as you approach from the left. I know it's weird because you're going right, but you're approaching from the left. Continuous on -3 to 3, this function here. Because it is defined at 3, you can plug in 3, right? You get an output of 0. You can plug in -3, you get an output of 0. Okay, pretty straightforward. There's the intuitive definition and the formal definition. So if I ask you to explain why something's continuous, you want to do this. You want to explain that this exists, this exists, this exists, and they're the same thing. That's the best explanation for being continuous at a point, and you can expand that or extrapolate that to the entire interval. And that's it really for continuity. We have trig functions. They're continuous everywhere on their domain. Here's your secant function, right? It has all those vertical asymptotes or undefined points for the secant function. That's at odd multiples of pi over 2. But everywhere else it's going to be continuous. And that's true for all of our trig functions. Of course, sine and cosine have the domain all real numbers, so they would be continuous everywhere for all real numbers because they're continuous on their domain. These four, of course, have domain issues, if you remember from trig. Okay, intermediate value theorem. Last topic about continuity. We can talk a little bit about kind of a consequence or a result we get from continuity, which is pretty straightforward. Not the most useful thing, but useful in certain cases. So the intermediate value theorem goes like this. If I had to draw, let me kind of start from scratch because it's a pretty straightforward thing. If I say, okay, if I gotta, let's say I want to guarantee that there's an output of, let's call that 5. Okay, and there's some function here, and this is f of a, and this is f of b. Now, if I told you that f is continuous on AB, then is there some value C, here's the question, is there some value C somewhere in the interval, can be anywhere, such that f of C equals 5? That's my question to you. What do you think? If f of A is down here, I don't know what it is, but it's less than 5. F of B, that is the output, right? Those are outputs, is greater than 5. In other words, do I have to hit 5? Is there any way I can draw my function f so that it doesn't cross that line? And the answer is no, it's got to. I could try and avoid it, but I got to get up here if f of b is the output. Okay, so that's what the intermediate value says. It says if f of a is less than a certain number and the other endpoint's greater than, or vice versa, then it's got to go through that point. Okay, it doesn't tell us what the outcome is. Or I'm sorry, it doesn't tell us what the input is, I should say, because we'll be asked about the output. It doesn't tell us what C is. It'll just say that C exists. It's called an existence theorem. Okay, here's what it looks like formally. If f is continuous on A, B, and L, that was my 5, is a number between f of A and f of B. Between means that it would have to be like f of A has to be less than L, and f of b would be greater than, or vice versa. I guess f of b could be the low point, and f of a could be the high point. That's what it means, of course, to be, mathematically, to be between. Then there has to be at least one number c such that f of c equals L. There has to be at least one number such that f of c is this, right? And that happens in this graph right here. That's where my c would be. I have to move them down. So in this case, f of c equals 5. And the whole at least, what's the deal with the at least thing? Well, if my function could also do this, right? Think trig function. It's not just, there's not just one place where f of c equals 5. There'd be a bunch of inputs that equal the output. Okay? So here's a case where the intermediate value theorem does not apply. You would say, well, here's f of a, here's f of b, here's f of a and b, f of a, f of b. It doesn't hit L in this case. You say, well, what's going on here? Well, it doesn't satisfy the conditions of the intermediate value theorem. F is not continuous. So there's no guarantee it could happen, but there's no guarantee that it will happen. Let's do one more example and then we'll be done with this section. It's a pretty short section. Use the intermediate value theorem. I need to show you the function. To prove that there's a root. Okay, so in this case, root means 0. So we have to show that there exists an output of 0. So L is 0. All right, so if I want to use the intermediate value theorem, I got to check my conditions. Condition 1, is it continuous? Yes, f is continuous, and I could say, well, polynomial function. We know polynomial functions are, now we know they're continuous on their domains, which are all real numbers. Okay, so if it's continuous on the real number line, then it's certainly continuous from 1 to 3. Okay, and then the next thing you say is, well, you calculate f of 1, and then you calculate f of 3, and if 0 lies in between these two outputs, then we're done. We say, yes, the intermediate value theorem applies, right? That's the other condition. It has to be between, that is, the output of 0. We don't know what the input is. This is an output, this is an output, right? These are the inputs. Is 0 in between? Well, let's find out. F of 1. We can do this in our head. 1 minus 2 is negative 2. Plus 3 is 1. Minus 21 is negative 20. Hope I did that right. Maybe we'll double check. Oh, this one's going to be harder. 3 to the 4th. Minus 2 times 3 to the 3rd is 27. Plus 9 minus 21. Oh boy. 81 minus 54 plus 9 minus 21. Probably should use our calculator here. But I think, let's see, 90 minus 54 is 46. Minus 21. I might have messed that one up. 46 minus 21 is, let's see, I think that should be